Okay, so you can keep track of time here as well. I will press start, and that should be. You can press S, and that will start the timer.
Oh, wow, that's
The
nice.
ambition is to have like 5 minutes for questions.
Have you turned it on?
No.
Oh, so it's the other way. Yeah. Perfect. You
Okay,
want to
I
probably
did not turn
adjust
it
the
on.
mic probably closer to. It's currently on mute. Sorry, this one.
Ah,
Okay. Yeah.
should I
Want to? Yeah. Want to bring it closer? Yeah. Speak now.
1, 2, 1, 2, testing.
Yeah. We still have some time. We have 4 minutes. Yeah.
I guess you will start the live stream at...
The live streaming is on. Yeah. Yeah. It will be on like 2 minutes before the. Okay. That's it.
Great. I don't like walking around with a hot mic.
Sorry.
I said I don't like walking around with a hot mic.
Okay. Turn it on. Yeah. Just remember to turn it on. That's fine.
I'm sure it'll be obvious if I didn't turn it on pretty quickly, yeah.
And then somebody from the audience is going to throw something at you.
Yeah. You have to be really mad, yeah. I mean, I think I wouldn't need it. Like, I wouldn't need it for the online audience.
Uh-huh.
I can project. I know how to project.
Okay, good.
I'll be nice to the online audience.
Good. Yeah.
And,
Online audience says thank you for that.
and maybe I can mumble.
If you want to be in a zone, I'll just step outside.
If you want to what?
If you want to be in the zone of giving a talk, some different.
No.
Is it already done?
No.
You can do that, right? If you want to. Only if you want to. You just need to press S to.
Yeah, that's my plan. I'm gonna do that. Yeah.
Hopefully it will work.
Yeah, hopefully it
Should I
does.
try it?
Sure, but then I don't know how to undo it.
There will be a 1 second delay.
Oh wow. Okay, I'll remember that. I get an extra second.
I'm really teasing you, sorry. I just should not do that before your talk.
Oh, it's fine. It's fine.
All right. Welcome back, everyone, for the second session this afternoon. So we will have 3 talks, roughly 30 minutes each. The first talk will be given by Orzel, and he will talk about the submultiplicativity of the subconvexity of Kronecker words of Set-Multilinear Polynomials. So can you please take over?
Yes. Hello. Thank you for reading that. Yeah, it's a little bit of a mouthful of a title. So I'm Ian, as was said. I'm a PhD student of Strassen and Radu. So today I'm going to be presenting a joint work that includes many authors, many of which are here right now. So we have, oh, this worked. Well, this worked during testing, but it doesn't work anymore. So that's Brand, Kronecker, Kasky, Lee, Seppelt, and Wang. Yes, so I'm just going to get started, and hopefully this works. Oh, I didn't press S. Okay, so today I'm going to be, this talk is going to be on tensors, but I decided instead of talking about tensors, I'm going to just avoid talking about them and just talk about set-multilinear polynomials. They're the same thing, basically. So a set-multilinear polynomial, I'm assuming you've probably seen it before, but it's just a polynomial where I can split the variables into d sets, and basically each monomial will have one variable from each set. A simple example, which you saw this morning, is the permanent polynomial. And here the sets can be defined by the rows of the matrix that we take the permanent of. So here we have, oh, it works now. Here we have, the first row, the second row, and then the nth row being the different groups of the variables. Okay, excellent. So another topic that we'll be talking about here is circuit complexity, which I really don't even want to mention it because I'm hoping that everyone here is familiar with circuit complexity. But I don't know, just for the sake of it, we have an algebraic circuit. It's a graph that has nodes that do addition or multiplication, and then we have variables or constants to be sort of the not leaves, but the nodes without any inputs. And yeah, you do computation in a pretty obvious standard way. And I can define the size of the circuit. I mean, there's many ways to do this, but I decided I like to be the number of nodes in the circuit. And then I have the complexity of a polynomial is just the size of the smallest circuit computing the polynomial. And sometimes I'll refer to it by this C function. Yeah, this is just syntactic sugar. Anyway, so I guess the first interesting thing I want to talk about that this talk will talk a lot about is called the Kronecker product operation. So I'm going to assume you've likely seen the Kronecker product with matrices. So I kind of wrote an example here with a matrix. So what is the Kronecker product? So if you have the Kronecker product of two matrices, it's essentially going to take the second matrix and multiply it by each coefficient, each value in the first matrix, and then sort of flatten it out into a larger matrix. So the Kronecker product of two 2x2 matrices gets flattened out to a 4x4 matrix. One should observe, pretty importantly, that it's still a matrix. The result of the Kronecker product of two matrices is still matrices. And this operation can sort of be generalized to tensors. Or for our case, we can generalize this to set-multilinear polynomials, assuming that the two polynomials are the same degree. And how this looks when you actually study it in a polynomial is basically we sort of pair the variable groups together. So here, this first polynomial has sum over x's, and then this one has also x's, and then when we take the Kronecker product, we sort of merge the underlying subscripts in our sets. So here we had a sum over i's and k's, and now the i's and k's are sort of merged in on the variable. Okay, and this is a sort of natural operation for tensors. It's pretty nice. It's submultiplicative for tensor rank. But for this talk, we're actually going to talk about circuit complexity. And the question that, one of the questions that we look at in this paper is circuit complexity submultiplicative, is Kronecker product submultiplicative over circuit complexity? So i.e., if I have two polynomials, I take the Kronecker product, and I have a circuit of them, does that mean that is the complexity upper bounded by the product of the complexity of each individual polynomial? So this is the question that we really want to look at. Okay, so why am I even asking this question? Well, I already mentioned that there's this tensor rank operation, which I'm not going to define, but hopefully you've seen it before, and we get submultiplicativity from that. But also when d equals 3, we have submultiplicativity for this operation. So this is a result of Strassen. So Strassen basically showed that when d equals 3, circuit complexity and tensor rank are asymptotically the same, and so therefore we immediately get submultiplicativity. So the question is, could we hope that maybe for d equals 4 or higher orders of d, could we get submultiplicativity? I need a simpler way to say that, it's a mouthful. Okay, so what are the results I'm going to talk about today? So I have 3 main ones that I want to talk about. So the first result in the paper is that if we have submultiplicativity for d equals 4, then we have omega, which denotes the matrix multiplication constant, will equal 2. So which is a very, very strong result. This may look, things get worse though if we assume submultiplicativity for all d. If we have submultiplicativity for all d, then VP would equal to VNP. And then if we relax this a little bit and let's say, okay, I don't want submultiplicativity for every d, instead I just want for some large d that maybe we have submultiplicativity. And in that case, you get this sort of interesting condition where you get a circuit for the permanent that is still exponential, but we've decreased this sort of exponent in the exponential. So let's just say it's 2 to the 0.99n. And generally, this is sort of, you could see this as sort of like an algebraic analog to the exponential time hypothesis, in that we generally, one could guess that this might not exist. But yeah, these are the results I want to talk about. Okay, that was the beginning. Okay, great. So to do these results, we're going to talk about this object called graph tensors, or that's what we call them. So this is what we're, all of our results are going to come from studying these objects. So what is a graph tensor? I felt that it was easiest to sort of try to explain it through an example. So let's just do that. So the general idea is I'm going to associate graphs with 0, 1 set-multilinear polynomials. So set-multilinear polynomials with 0, 1 coefficients. So what do I do? So I'm given some graph. Here I have an example graph. It's a grid. I don't know, this is a 4x4 grid. Fine. And now I'm going to associate with it a polynomial. And the polynomial is going to be a sum over all colorings of the graph. So here I'm going to use this sort of second subscript to denote the number of colors. So here we just have 2 colors. So the graph tensor is going to be sort of the sum over all 2 colorings of our graph, where the variables, I have this really big table here, but each node is going to get assigned a group of variables. And within the group, the variables are going to be given by the colorings of the incident edges. So what does this table mean? So let's say we pick some vertex v22, then we define the variables x, v22, and then as a subscript, we give the coloring of its adjacent edges. So for instance, we could have colored them all red, or maybe we color the right one blue and then the rest of them red, or maybe, I don't know, these 3 are blue and this one's red. We get a variable for each coloring, and then all you do is, the actual tensor, or the set-multilinear polynomial, is just going to be the sum over all colorings, and then the product of the variables that are associated with this coloring. And by associated, I mean that this sort of subcoloring is consistent with the full coloring of the graph. Okay. And these are nice. They have some nice properties, so I've sort of written it already. I've spoiled it with this table. So the first observation is that we can use this to count the number of matchings in a graph. And how do I do that? Well, I just save the variables that have exactly 1 blue edge. And then I kill off all the other variables. And then I can count the number of matchings, because now all we're left with is every vertex has exactly 1 edge associated with it. I can also do something similar with 2. If I was interested in having 2 blue edges and 2 red edges, I could count cycle covers. And I guess the idea is within this set-multilinear polynomial, we actually have a lot of interesting properties of the graph sort of embedded into them. And we're going to use these and study them for specific graphs to get interesting results for set-multilinear polynomials. Yes, I'm hoping this is clear. So let's do examples. I like examples. So the first example is a triangle. So very simple graph. So now let's assume, earlier I was just doing 2 colors, but in general you can define it for n colors, let's say. And then so I could define the triangle graph for n colors and ask what is the associated graph tensor to this. And maybe if this was a longer talk, I could ask someone what this would be, and then maybe someone would see that if you write out this tensor, it looks something like this. I have this sort of color-coded by the edges, so you have this, for instance, I goes with x, assuming that, let's say, x was this vertex, and then y would be this vertex, and so on. That this is just the matrix multiplication tensor, if you've seen it before. If you haven't seen it before, then this is the matrix multiplication tensor. Okay. And a quick observation I make real quick that will become useful later is that this, the complexity of this is n to the omega by definition. So this is sort of where theorem 1 is going, is that triangles are n to the omega. I'm hoping, people have seen this before. Okay, excellent. So now I also want to talk about some of the properties of these graph tensors and why they're sort of nice to look at. And one simple sort of operator that I can do on these graphs that sort of works nicely with graph tensors is what we're going to call the sum of graphs. I don't actually know if this has a better name. I'd love to hear it. But let's say the sum of graphs. So what is the sum of graphs? So let's assume we have 2 graphs. They're going to have the same set of vertices, but a disjoint edge set. And the sum is just going to be, I lay over the 2 graphs on top of each other. So I haven't really mentioned this, but I'm sort of assuming I have access to multi-graphs, so they can have multi-edges. Okay, great. And this is really nice because it turns out that taking the sum of 2 graphs exactly corresponds to the Kronecker product of the 2 polynomials. So essentially from here on out, we should be able to not have to talk about Kronecker products, we can just talk about the sum of graphs. And the proof of this is very easy. I think it's sort of nice to just talk about it really quick because it also gives more examples for what a Kronecker product looks like. So here I have two graphs. I've sort of labeled the vertices x, y, and z, and I've sort of labeled these edges. And then I can look at what their corresponding graph tensors. So for instance, x has subscript I and j because it's adjacent. It's incident on those two edges. And then I can take the Kronecker product with them, which merges these variables. And the key observation here is that this is the same as this overlay. And it's really mechanical. I mean, this is exactly what we're doing, is we're just sort of overlaying the two things. Yes, okay. Excellent. Yes, some more facts that are interesting that we'll use here is that, actually if you have vertex disjoint graphs, and by vertex disjoint graphs I'm sort of, I mean that ignoring vertices that don't have any edges, then you actually get an upper bound on the Kronecker product complexity by the sum of the two complexities. And this follows from what I said previously. And the reason this is interesting is because one of the big tools that we're going to use for these proofs is the k-matching. So let's let our graph be a k-matching, which just means we have k independent edges in our graph. And then the key observation here is that we can upper bound its complexity by nk. So it's actually, we can pretty efficiently compute the k-matching graph tensor. Okay. So this should be enough for talking about graph tensors, that we can now start to talk about some of the proofs of our results. And I'm hoping from showing these proofs, I can sort of show how these graph tensors are useful for proving these things. Okay, so let's do theorem 1. So recall that we now have submultiplicativity over 4 tensors. And if this were the case, then I'm just going to pick some graph. So let's pick a square. I guess I observed that the square can be split into two matchings of size 2, which means that I can compute this graph tensor in O of n squared time. Yes. Okay. So now we want to reduce this to matrix multiplication. And recall, matrix multiplication is just a triangle. So the idea will just be to sort of condense one of the edges. And this is very easy to do. I mean, if you just look, if we write out the graph tensor fully, the idea is we can sort of set this last variable to force its two indices to be the same, and this sort of contracts the edge, and then we get a triangle, and that means we have an n-squared algorithm for an n-squared circuit for matrix multiplication, which would mean that omega is 2. Okay. Yes. Hopefully that's clear. Okay. Okay, great. So let's talk about the second one. So this one assumes that, let's assume that we have submultiplicativity for every d, and now we want to show that p is equal to np in this case. Okay, so how do we do it? Well, now I'm going to bring back these grid graphs. And let's say we have some k by k grid, and I want to study the graph tensor corresponding to 2 colorings on this k by k grid. Okay, you might have seen it coming from the last one, but I can easily split this up into a bunch of matchings, 4 matchings. And now once I have 4 matchings, I get a polynomial circuit in K for this graph tensor. So therefore, assuming some multiplicativity, I have a very simple circuit for this graph tensor. But the next part of the proof is I'm going to reduce this to the permanent. And this is a little bit technical. I won't talk too much about it. But the high-level idea is what we're going to do is we're going to take this. So recall that currently we're taking a sum over all red-green colorings of the grid. But now what we really want is we want to have a sum over all of the permutations of n. So what we need to do is we need to sort of assign different permutations to the different to the grid, to different colorings of the grid. So for instance, I have a permutation here, and I know it's a mapping 1 to 4, 2 to 1. I don't know, I picked it arbitrarily. And the idea is that I now want to convert this into a coloring on the grid. And there's this very nice idea to do this, and that's just I sort of imagine that the x-axis is sort of inputs and the y-axis is sort of outputs, and I imagine that I sort of drew a line starting from the input up until I hit the output, and then I went right across to the output. Yes. And then if I do that, now all I need to do is just kill everything that doesn't look like this. And this is pretty, this is pretty simple. All you have to do is just kill every, because if you recall, the variables are associated to their incident edges. So to kill all the bad things, I just have to kill things that don't look like this, that are vertical, horizontal line, a crossing line, empty, or to the right corner. And this is it. This is the proof. Now I've reduced this to the permanent. Yes. I do want to note here, there is actually, so a reviewer for CCC actually pointed out that there was a simpler proof of this fact, which is very nice. It uses, I won't go into it, it uses a different strategy, but I just wanted to mention it that, you can, if you take the tensor product of two determinants, you get a similar idea. But here, I guess the interesting thing is we've used these graph tensors and we've sort of constructed this using 0, 1 tensors only, whereas with the determinant we sort of needed to use -1 and 1 and have them sort of multiply to get 1. Anyway, I don't want to talk too much about it, I just wanted to mention it because I thought it was cute. Cool. Anyway, theorem 3, I actually have more time than I expected to have. I think maybe I'm going fast. It's okay. So theorem 3, I want to talk a little bit about this. So for theorem 3, now we only have a very large k. So now we don't know that for every, we don't know submultiplicativity for every d, but now we have some large d. So we know that there's some large grid. I have some efficient computation for it. Okay. So, but now I want to say something about a much bigger grid. So yeah, way bigger grid. And the idea is I'm going to want to take this big grid and reduce it to a small grid using vertex contraction, where the idea will be I will take some subset of vertices and contract them into one vertex. And I'm going to repeatedly do this process until eventually I convert my big grid into a small grid. So I don't want to talk too much about it. But if you can sort of math out exactly what the cost is of sort of contracting a bunch of vertices. And then we just do this nice strategy where you can just sort of slowly, I'll just show the whole thing. You can sort of slowly take your big grid and merge vertices over and over again until eventually you can take a big grid and it'll become multiple copies of some smaller grid, which is our nice grid that we know we have nice properties of. And then if you go through the computation, again, for this talk, I don't want to go through the computation because, it's not especially an interesting computation, but this is just a high-level idea. You'll get some savings in your reduction to the permanent. And so this gives you a slightly smaller than 2 to the n circuit for the permanent. Yes. Okay. Cool. So we talked about other things in this paper as well. I didn't have time to go through all of the results, but there's lots of cool things in this paper. I just wanted to briefly mention some of the other ones that we use the graph tensors for to maybe get you to look at the paper. So anyway, what's the idea? So the first result that we have is that, so for D tensors, we get an upper bound on the asymptotic tensor rank, which I haven't talked about, and I don't want to define it for this talk, but it's just some nice, it's some function on tensors that sort of describes their behavior as you sort of Kronecker product them up into higher tensors. Again, I don't want to talk too much about it. But we get a better than what was known upper bound of n to this exponent. This is some decimal exponent. So we get a better upper bound for that. Another thing we do in this paper is we sort of take this definition of asymptotic tensor rank and sort of expand it to circuit complexity. So now we can sort of talk about asymptotic circuit complexity. You have to be a little bit careful so that it's well defined. But with this sort of care, we sort of define this quantity, and then we sort of ask the question, how can we upper bound it? So we first got a general upper bound for all tensors, which is given here, which you should observe is better than what we have for the tensor rank, the asymptotic tensor rank. And then we also did some computational studying, some for d equals 4 and d equals 5 to see what upper bounds we could get for the asymptotic circuit complexity. But anyway, these are just the results from the paper. Okay, so that was all I wanted to say. So in conclusion, our results sort of show that this is probably not submultiplicative, even if we have it for, it's probably not even submultiplicative for d equals 4, let's say. We also wanted to establish that graph tensors are pretty cool. I recommend, that's maybe one of the big takeaways I want to give, is that through looking at these graph tensors, we were able to get these results, and that we hope that looking at these more can give even more interesting results on tensors. And we're at CCC, come see us. Robert Andrews was smarter than me to put up a QR code for the paper, and I didn't do this, but it's in CCC. That's it. Thank you. Done a little early.
Can you embed other measures like slice rank, partition rank, etc. in this framework of non-trivial asymptotic upper bounds?
So we haven't thought about it, is my answer. But I mean, I'd imagine you could. I mean, you could. I mean, they're just tensors, so I mean, you could put whatever measure you would normally put on tensors onto these sets of tensors and see what happens. But I don't know what would happen. But it's a very good question. But the answer is I don't know. But you could. Cool.
Have you thought about subadditivity for circuit complexity for these things?
Sorry, subadditivity?
Yeah.
What would you mean by subadditivity? Like,
I guess you would need to, I mean, you can have direct sums of tensors.
Okay, we haven't considered this. It's a good question, I guess. So, I mean, I guess this is sort of what we were talking about. Yeah, I mean, the result I sort of was talking about when you have sort of disjoint graphs. I guess this would be sort of like a direct sum. But I don't know. That's a good question, though. Maybe we can talk about it later. But I think, we haven't thought about it.
Thank you for the nice talk. It seems that it will be hard to apply asymptotic spectrum theory of sampling on this field because of the submultiplicativity. But there have been several generalizations of the asymptotic spectrum theory from the sampling to semigroup. Have you tried to apply such a theory for this subject?
No, so I'm not super familiar with this actually, unfortunately. So I can't talk too much about it, but I don't know anything about looking into that. But it's a good question.
I think we can take one more question.
Yeah. So I wanted to ask you about. If you have any explicit description of like any such tensors, in the sense, or can you describe them as like an array of like numbers, for instance?
I mean, so you would basically, basically, these tensors are, you can imagine the indices being. So you have one index for each vertex, and then the entries are just these colorings. So I mean, this is sort of, I guess this is just exactly this description, right? I
No, like I wanted to ask you if you already had explicit descriptions, or like have you never thought about making such one?
I'm confused by the question.
No, like have you actually computed any such descriptions of the tensors?
I mean, I've never like done.
Okay, yeah,
I haven't done any computation with them really, but I mean, yeah, I mean, I can write. I've written some tensors on hand by hand.
I wanted to ask about this because there are some nice bounds about the tensors, and maybe like these could be used as some counterexamples in some other things.
Okay, yeah, it's a good question. Yeah, I don't. Yeah, that's.
Okay.